Shall I begin?
Yes.
Yes, Mark, you got it. We got a great connection.
Okay, thanks. Well, I want to say it's a real pleasure to have the opportunity to phone in, and I'm really disappointed that I'm not able to be there in person. Needless to say, this paper has been sort of an inspiration for a large part of my career, and I, at various times, have probably struggled with, very naive questions about how to interpret this phenomenology, and I'm sure I would benefit from the wisdom in the room. So Lev asked me to give a summary of the evolution of the idea for efficient interaction-free measurement, which was published in this paper back in the beginning of time in the mid-90s. And so I happily agreed. I don't think I have too much really insightful to say, and it's like super dangerous to go back in time, especially when memories can fade and so forth. But I have to say that at this time it was early in my career as a faculty member at Stanford, and I was very lucky to have been invited to visit Anton Zeilinger group then in Innsbruck. And at the same time, a numerous, really inspiring people were also visiting. And I mentioned Paul, who I think is in the audience, of course, Harold Weinfurter, and I think Lucian Hardy was there in part. And it was just sort of, it was one of those, moments in time that when you look back in your career, you're like, wow, that I was very fortunate to have been able to have been surrounded by so much, kind of just inspiring conversation. And when I arrived, one of the topics of conversation was the interaction-free measurement paper. And the discussion point was, is there a way of rendering that more efficient? We all know that the bomb tester is great a fraction of the time, and that's already fantastic and has, I think, already, some pretty remarkable potential practical applications. But the question was, is there a way of bringing the efficiency of such a measurement closer to unity? And I guess, well, the scheme published was is shown in this illustration, and the idea is successive coherent interactions can be interrupted by an absorber, and therefore change the coherent evolution dynamics from output 1 or to output 2, or detector D1 clicks or detector D2 clicks, and in the limit where you have a large number of stages, this can be the efficiency of such a scheme, neglecting practical losses, can be nearly unity. And to me, it's remarkable that quantum mechanics lets something like this happen. And I struggle with the analogical implications of that, in terms of how we think about wave functions and all the rest. But also, what amazes me is this idea of repeated interrogation, coherent interrogation in the presence of loss has deep applications, I think, in, for example, microscopy. And I want to say a few words about those applications after I finish this reminiscence. So I would say, going back in time, what were some of the ideas that we had in mind when considering this question, how to improve efficiency? And for me, there were, I think, three important inputs. Input one was the idea of quantum jumps. And this was something we have to, this seems trivial now, but, back in the early 90s, and in this was out of Dehmelt's group in the mid 80s. These ideas were, kind of astounding, and especially their experimental realization. So let me just take you through this classic paper from '86, Warren Nagurney and Dehmelt and John Sandberg. So you have this ion level scheme as shown in left. And this was back when it was a struggle to get, excellent lasers. And so the way this worked was there was a strong laser shown in the dark black line that excited and allowed optical transition. And when the ion was in the S1/2 state, and this strong laser was on, it would fluoresce, and you would see a lot of scattered light as shown on the diagram on the right. There was also a lamp at 455 nanometers that could make a transition to the P3/2 state, which was long-lived and obviously out of the cycling transition for 493 nanometer light. And when that transition occurs, then the remarkable thing is the fluorescence is just suppressed. And so you see a drop from, so I guess it was 1,500 counts per second down to the noise floor of the detection system. And then the system would, randomly jump between these levels. And so you're asking, what's the connection with this with thinking about efficient IFM? Well, if you start wanting to be quantitative about, when those gaps occur, when those jumps will occur, and you want to do so by, comparing the relative strengths of the coupling to the detection laser, I would say that 493 transition that gives you the fluorescence, and the coherent interrogation laser, the 455 nanometer, excitation, you basically come to sort of the conclusions that have been popularized by this paper, the Wineland, it's Atano, Heinzen, Bollinger, and Wineland, and their quantum Zeno paper. And this is a paper now kind of, in my view, visiting that same electron shelving work, but now in a system where rather than being forced to work with lamps to excite the metastable state, they had a more judicious choice of energy levels and so forth. And what they observed was what we all know is the classic quantum Zeno result, which is, in their case, the metastable transition was between two microwave levels, the ground state, state 1, and the excited state, state 2. And then the fluorescent or detection state was on the 1 to 3 transition. And so they would leave on the coherent couple after state preparing in either state 1, or they could state prepare in state 2. Then they would look at the transition probability as a function of how many times they interrupted that transition probability by pulses of light on the 1-3 transition. And their data is shown on the lower right panels. The center panel is when they leave the initial state of the ion is initially in state 1, and then they turn on the coupling, the coherent coupling, to state 2. And then while this coupling is on, they pulse on the 1 to 3 transition, and that sort of interrupts the coherence. And what you see in the histogram is that the transition probability, as the number of interrupting pulses is increased, suppresses dramatically. And that's been interpreted as a manifestation of the Zeno effect, where if you observe which state the system is in, then it can't walk away from that state. I think from the point of view of thinking about efficient IFM, the second graph is on the lower right is maybe more relevant, and that is if you start the system in state 2, so it doesn't want to fluoresce in state 2, but you turn on the coherent coupling, and then while you do that, if you don't turn on the detection laser, then you get you've tuned the system so you get kind of unit transition probability down to level 1. But then if you turn on this detection laser, this interrupting laser, then for the given number of pulses, you can again interrupt the coherent transition, and basically with this absorptive channel, you can basically suppress the Rabi flop between level 2 and level 1. And so, and you can do that with a negligible loss as the number, gets very large. Now, in practice, in the paper which I reread yesterday, they mentioned they had some optical pumping backgrounds or whatever, so they were never able to do more than 64 pulses. But I think the idea is there. And I think this is very strongly analogous to the efficient IFM scheme. And then there was, and I mean, you say, like, I would just say that these ideas were, if you were in a spectroscopy group, or, I was in my PhD with, to just finish my PhD with Steve Chu in the early 90s, these were the ideas that were being discussed. And so it was sort of natural to extend the IFM idea and think in context of these quantum jump systems. And like the final background, and this is just going to, I don't know how really to cite this or to talk about how this idea came into the discussion, but kind of this may have been out of group discussions with when I was a PhD member in Chu group, or it may have been something that was being discussed with Paul and others when we were in Innsbruck. But you just have this marvelous result from classical optics, polarizers, that you can basically rotate the polarization of a beam of light with a sequence of projective polarizations where the projection angle is slowly incremented. And so working across this admittedly crude diagram going from left to right, you start off with, you have cross polarizers. And the idea is if you have a photon coming in from out of the page, it can't make it through those cross polarizers and nothing will click on the other side. But then as we, this is a demo even that I run in my intro E&M lecture, you say like, oh, look at this. Let's put a polarizer at a 45-degree angle between the cross polarizers. Then you know that some of the time light gets through. and then this on the right-hand side is something I don't put in the intro E&M lecture, but an extrapolation is you solely can rotate the axis of that polarization. And of course, each time you're doing a little bit of projection, but also what's happening is the polarization plane is rotating. And so with a sufficiently large number of polarizers, I can rotate the polarization and also do that with minimum loss just using an absorptive polarization element. So those were the ideas, and because this is a reminiscent, I don't even feel like I have to explain how those ideas, like sprung together. But I think it was the basic idea is coherent evolution can be interrupted by sequential absorption, and then from the point of view of mapping this onto kind of real world experiments. The challenge was, how do you devise an apparatus that lets this happen and also in a way that's consistent with the technology you have at the time. So that's sort of what I wanted to say about that, the evolution of that idea. And I'm really grateful for Lev for asking me to go down memory lane in that way. And as I said, this idea of efficient IFM has come back and forth at me throughout my career, sometimes accidentally. And the most recent incarnation is in the context of microscopy, where now more than a decade ago, a Moore Foundation program manager knocked on the door of my office and said, well, somebody has this proposal out there for doing non-destructive electron microscopy, and it references this paper that with Paul and you from back in the 90s. What do you think about that? Is it possible to do non-destructive electron microscopy? And he's like, I'm a biologist, and if we could detect cells and make movies of what's happening inside a cell, then but without destroying the thing with an electron microscope, this would be an amazing advance. And so, as the experimentalist who can't resist a challenge question like that, we started thinking about that in collaboration with numerous others. Moore Foundation stood up a collaboration with Peter Hummelhoff and Peter Cruitt and Carl Bregan at MIT. And we just started brainstorming ways of maybe implementing IFM or efficient IFM-like ideas in the context of microscopy. So, as a pivot to that, this is not the scheme that we are currently pursuing for the electron microscopy, but I think it's here's a recent paper that it's probably in print now, but a few years ago we pulled it off the server, and this was drawing a connection between diffraction and IFM. And that immediately rung a bell. It was directly relevant to some of the optical work we had been doing in dark field microscopy. And, in my view, it established a really nice connection between IFM formally and the idea that in a dark field microscope, where the blue is the illumination beam and the scatterer, which can be absorptive, scatters the purple beam of light, and if you go with a stop and block the illuminated radiation, then the purple light can be refocused on a position sensitive detector. And if you think about this on a single photon level, you come with the idea that some of the time, you'll get the click on the camera, and you get that click. So the photon is there, so it wasn't absorbed, and so you detect the presence of that scatterer, quote, without damage or interaction. Of course, that's those are not quite accurate words, but this is just a way of thinking that, hey, maybe there are some strong analogies between what we've been calling interaction-free measurement and some of the protocols that we envision in microscopy. And so this is not exactly what we're doing in the lab today, but I want to use this as just a kind of a formal pivot from IFM to the idea of kind of quantum optimal microscopy methods. And in these quantum optimal methods, the challenge problem is a little bit different from like, let's detect the bomb without blowing it up, but not so much different. So in most microscopies, your goal is to, at a pixel, detect some small object. I mean, it could be a red blood cell, it could be a protein in electron microscopy, it could be a single atom in electron microscopy. And that pixel is associated with a phase shift. Yeah, in kind of the schematics that we draw in concept foundations of quantum mechanics, it's just a plate that's a phase shift. And then it also has a finite probability for absorption. So it's not like the perfect bomb. When the photon illuminates this pixel, it gets phase shifted, and there's a chance that the bomb goes off, but most of the time it doesn't. And the name of the game is to get as much resolution on measuring that phase shift without blowing up the bomb, without suffering an inelastic absorption. So here we're changing the physics. We're allowed to measure phase shifts in addition, and to think about phase shifts, and that is sort of the key observable. But we want to do it in a way where we minimize the amount of inelastic scattering. And so, just by way of thinking like a microscopist here, we developed this protocol several years ago, which we call a multipass protocol, where if you take the probe particle and you pass it through the scatterer multiple times, I mean, what we would say is the phase shift increases, like linearly with the number of passes. And in a dark field microscope, it turns out that the intensity that's observed at, or the probability of observing a photon at a position on your detector, basically scales as the phase shift squared. And so if I go through the image target m times, the probability of detecting that thing goes as m squared, phi squared, where phi is a single pass phase shift. And if I want to say I detect it, well, basically you want to have detected a single photon, so that probability times is small on a single pass maybe, but I mean a single interrogation, which could have multiple passes, but I'm allowed to shoot a number of probe particles at the image target, and I just keep on shooting them until I eventually see a click, and then I say, oh, I've detected the thing. And then you can say, well, if that's my protocol, I interrogate until I damage. I interrogate until I get the click. That tells me that there was something there. What's the probability that I had a damage event during that interrogation sequence? And there's some more simple arithmetic we can do, because if I say there's an absorption coefficient alpha for a single pass, if I go through it m times, I have m times that absorption coefficient probability for damage. And if I have n particles that I've used in sequential interrogation, that's the total damage. And so just like substituting in and rearranging symbols, what you can find is that if I can interrogate the sample multiple times where, where M is a large number, then I can basically strongly reduce the damage probability for detecting that object. And what I have a few more slides to show before I reach this conclusion. But what can get exciting is we can get to a point where the efficiency of such schemes, we think, may be such that we can be in like a quantum non-demolition regime where we can by detecting the photon, know that we haven't ever damaged the particle with an inelastic interaction. And so therefore sort of drawing an analogy with some of the ideas of efficient IFM. So, just to show you that some of this can work in hardware, and I realize I'm going pretty quickly, and I said I only needed wanted a half hour to speak. So there's a lot of ideas out there, and many of them have been tried in experiment. Kind of one of the challenges in doing these multipass microscopies is, which is sort of like the challenge of building an efficient IFM, is figuring out a way of getting the probe particle to go back and forth between your sample multiple times. And so the layout you see on the bottom of the slide is the conceptual schematic of what exists in the lab. And as you see in the center, a couple of microscope objectives. The sample sits right in the middle there, and then there are ways of coupling light into this quasi-resonant cavity where a pulse of light can bounce back and forth between the sample. And then there's a Optical cell which lets it couple out the pulse of light and then send it to an imaging detector. And this is the way we can, kind of sequentially interrogate a sample multiple times and then form images. And what's surprising is, like when you first describe this idea and you don't show data, people say, well, that's just like almost some theorist fantasy, because there's no way you can build a microscope and keep the aberrations low enough and the losses low enough that this would ever be practical. But it turns out that that's not the case. And with kind of modern objectives and low loss optical coatings, you can get to some interesting regimes for doing these multipass interrogations. And just to kind of show you how that works in practice, here's we're not in any quantum regime here. It's just let's pass multiple times through a single bead and show what the probability of, or the intensity of light in the dark field detection plane is as a function of the number of passes. And I claimed earlier that that intensity scales as the number of passes squared. And this is data showing that. And sort of the connection with efficient IFM is when I start thinking about probabilities, what I'm doing is improving the probability of, when I think quantum, I'm improving the probability of a possible non-destructive interaction. It's not just an absorbing sample, it's absorbing plus phase shift. So I'm sort of most sensitive to phase shift here, and I'm just worried about that absorber every now and then being the thing that blows up the bomb and ruins my sample. You can do that same thing with red blood cells. So this is what a red blood cell looks like in a multi-pass configuration. And it's, with just one pass through the sample, there's almost no chance of seeing the red blood cell in this dark field modality. But if I go back and forth 7 times, then the red blood cells are straightforward to see. Of course, you have to do a little interpretation because it's a complicated thing that's happening with the light, which is as it's going through this blood cell, which is several microns in diameter. But at the end of the day, I would say, hey, if I'm just interested in detecting the presence of a red blood cell, I'm certainly in a much better chance of doing that with repeated interactions. And then you can start to say, well, let's go down to single photon, single click level, and ask the question, like, can I get to a meaningful regime where the detection of a single photon can semaphore the presence of either a red blood cell or a 200 nanometer bead? And so that's what this data is showing. This is work in progress, unpublished. And, like the dream we're trying to live is ultimately, red blood cell in field of view. Is it? Well, we know it is if one click fires on a high efficiency photon counting detector. And to get to those kind of inferences, you would define regions of interest, or subsequently coherently manipulate the scattered light so that you can, that this complicated shape in the scattering pattern in the case of the red blood cell is reduced to something that can be registered with just, kind of one bit of information. And then making a transition to, so that's sort of what we're doing with optical microscopy. And you can also say, well, maybe you're interested in smaller stuff than red blood cells. And so we're building an electron microscope that exploits this multipass methodology to reduce the damage in detecting small proteins. And so this is animation which may not be animating well on your screen, that Colin Ophis from the National Center for Electron Microscopy at LBNL put together, where he simulates an electron column that we devised to basically do a multipass sequential interrogation of a nanometer scale protein. And there's lots of experimental details on how to implement this with charged particles, electrons, but it amounts to time gating electric potentials. And on the bottom part of the slide, you can see our schematic of how this is working in the instrument we're building. We gate an electron in, the wave packet rattles back and forth between mirrors, and then it's gated out. And with the marvelous electron optics design tools we have today, it's possible to keep aberrations at a minimum level. And then after the scattered wavefronts leave the exit beam splitter or gate, they can be manipulated either with a dark field scattering method, where we block the unscattered rays, or we can image in bright field or phase contrast. And it turns out that, and this is just where nature is being kind to us, that if you look at, say, this molecule, which I've recently learned you can download this stuff from the protein database, and it tells you basically everything the world knows about these complex structures. Well, these structures actually present as very quantum imaging amenable image targets. Like, they have small phase shifts and they have small inelastic losses. And they really, especially at high interrogation energy for the incident electron wavefronts, they really, in terms of parameters, fit really nicely into a regime where you can imagine doing a non-destructive detection. In other words, having the coherent interaction be dominant to the inelastic scattering. This slide is just showing that Colin Ophis played a major role in this. For different small molecules that you see on the left, you can basically look at what kind of images you would build up as a function of the dose, the number of electrons you send at that, as a function of the number of passes the electron can make through the sample, taking into account the coherent and inelastic losses. And the bottom line is you can get into some pretty interesting regimes that are currently unattainable with conventional electron imaging methods, where it looks like you can actually image small strands of DNA without damaging them. And this is relevant because when you put a strand of DNA in an electron microscope right now, it is completely damaged. And the only way you make inferences about the structure is you have hundreds of thousands of copies of the same small thing, and you stitch together the results of hundreds of thousands of interrogations to piece together what the structure might look like. So this slide just shows the hardware that we're building, and what's exciting for us is that we'll be in a position to start trying some of these ideas probably within the next 9 months. This is being built by a company in the Czech Republic in collaboration with a company in New Hampshire. And I won't take you through there are a million wires and electrodes and to make that electron bounce back and forth and do the imaging is a rather complicated task. And, there's some really exceptional engineers that are working this problem. But in conclusion, I want to just go back to maybe a more theoretical event and, kind of show you this plot, which was published in Applied Physics Letter in a review article we wrote on non-destructive electron microscopy. And here, we're going back into a sort of an IFM mindset. And we're asking, if we're detecting a particular small protein, and I won't tell you about how we modeled that protein, and including like all the loss associated when you build these electron microscopes, you have to support that protein in a substrate. In cryo-EM, it's this frozen liquid that contains the molecule you're looking at, and you have to consider the loss from that, and as well as the scattering properties of your image target. And modeling those using kind of the numbers that come out of the electron microscopy community, from the point of view of foundations of quantum mechanics, you can get into this I think remarkable regime. And we can ask the question, what's the chance of having a counterfactual detection of one of these proteins? And this is parameterized in terms of the thickness of the protein, which determines the ratio of the phase shift to the absorption. And we can do that for various imaging protocols. One of them is, and in this case, we're considering the multipass protocol, and considering single pass, which is the orange line on the bottom, and then what happens when you have an optimal number of passes, which is when you match sort of the number of passes to the absorption in the sample. And you ask the question, what's the probability of making the detection without anything inelastically bad happening? And with the electron microscopy, inelastically bad is really bad. That's like the bomb going off. And so we'd like to detect without the bomb going off. What's the chance of that happening? Now, also in electron microscopy, we have many identically prepared samples. So it's okay to have the bomb go off some of the time, as long as you know when it went off. Like, in other words, that the electron it damaged the protein, which usually means it doesn't show up your detector. Well, it turns out that going to optimal multipass for thin samples takes that counterfactual probability from something that's low, around between 0.2 and 0.3, and brings it up above 0.8, close to unity. You say, like, well, isn't 0.2 or 0.3 already pretty good? I mean, single pass, that's what an electron microscope can do today. But kind of where we want to go with this is to detect structures. And so in detecting structures, you don't just need one successful multipass. One successful counterfactual measurement. You need a whole string of them. Because I need like maybe 10 detections to know that I'm looking at protein A in conformation 1 versus protein A in conformation 2. And so you can ask the question, what's the probability of having 10 successful counterfactual measurements? And what I mean by that is inferred zero damage on the protein. And it makes a big difference whether that number, the probability of for a single counterfactual measurement is 0.3 or 0.8, because that number gets exponentiated. And so you can go from a situation where, with existing technology, where it's just hopeless to do a counterfactual, kind of say quantum non-destructive observation, to one where, 1 out of every 10 1 out of every 10 experiments, that's going to happen. And like from my view in quantum sensing, oftentimes in quantum sensing, we feel like we don't enjoy the exponential gains that the quantum computation community can advertise. But I think, once we start talking quantum sensing in terms of some of these counterfactual, quantum ideas, those exponential gains are also there for the sensing community. And I think there are a number of papers that are out there sort of starting to show that. So this is my second to last slide, and I guess I don't really want to go into too much detail into this slide, except to say that this is sort of coming full circle on the talk. Going back and asking the question, now I'm at the quantum information level and using Fisher information to ask, what's the best way I have of detecting a weak absorber with a phase shift? And comparing with quantum information and formalism, all the different schemes out there, and the jargon for those schemes are on the the axis labels on the right. Which it turns out that one of the labels, CIC, is a scheme that's very similar to the efficient IFN topology. There's squeezed light in there, and there's using noon states, and there's also just putting single pass probe through there. And the bottom line is, that sequential single particle interrogation with interferometric channels, like, kind of which is the essence of IFM and efficient IFM, it turns out that those methods from the quantum information perspective are just as efficient as using these massively entangled states, squeeze states or Noon states that we've been kind of in the quantum metrology community taught to think as the salvation of all our measurement problems. And so it turns out repeated sequential interrogation for imaging problems can be a very effective, dose-efficient way of gaining information about samples. And so, this is what some of the hardware looks like in layout. It's very similar to the diagram I put up on the second slide of the talk. And so I'll just conclude there with the idea that I'm very grateful for that initial IFM paper. It's an inspiring idea that we all in the physics community have taken in our own directions, and in my group now we're trying to pursue these more practical directions. And of course, I'm always deeply interested in the foundation's implications. So at that, I'll conclude and thank you all for your attention. Of course, the people who I've collaborated with and who helped do the work.
Right. Paul's got a question. Oh, here you have a question? Paul, you got a question. Let's go. Hey, Mark.
Oh, hey, Paul.
Beautiful, beautiful stuff. So it was a lot of material. So in your microscopy, when you're doing repeated interrogation, is that a discrete number of times you said for the Optical cell?
Yeah, well, the optical version, yeah, it's the Optical cell switches the light pulse in and then it switches it out.
Great. Okay. So I mean, I've done something similar, not for imaging, of course, but so that's great. The question is, there's this other way of doing IFM where you have two coupled cavities and you screw the impedance of the cavity, and so basically it's not a definitive number of cycles. It's an indefinite number, but you don't need to have a Optical cell. And I'm wondering if there's an advantage to this discrete number with the Optical cell, which of course has the problem of it has a freaking Optical cell, so that's a pain. As opposed to just doing a cavity arrangement. I'm sure you thought about is what's
well, I could talk about a half hour about that, Paul. I really appreciate the question. Thank you. And what's the fundamental difference between Q spoiling of a cavity and these kind of semi-resonant schemes involving switches is that I don't need to engineer the longitudinal coherence length of the source. So with a cavity, I always need to maintain the cavity resonance conditions. I need the coherence length of the probe to be, multiple times the length of the cavity. Whereas if I switch a pulse of light into the cavity, that actually can be an incoherent pulse. Like it can have very little longitudinal coherence, which from the point of view of microscopy is a huge practical advantage, because a lot of times long coherence length sources just basically mangle images because you get multiple scattering, and stuff that you didn't want to image ends up contributing to your image in ways you don't enjoy. And so if you want to see an example of this, we just put a paper out in Optical where we did flow cytometry with an incoherent source and multipass imaging, and you just can get amazing signal to noise, but without suffering the disadvantages of the coherent back reflections. I think there are some applications where I would rather have coupled cavities. So it really depends what like if I'm doing a measurement to detect dark matter particles, and the dark matter particles is something that's going to interrupt a cavity Q or provide a low phase shift, coherence is the way to go on that. But for the microscopy methods, this is why we prefer those Optical cells.
Yep, makes sense. Thanks.
Yeah. Thanks.
Hey, anybody else? That was fantastic. Thank you, Mark, very much.
Yeah, I really appreciate you guys listening to me just before lunch, and I wish I were there in person. Thank you very much.
Thank you. Bye. Bye.
Yeah.